So to kick us off, I'd like to introduce our first speaker, Dr. Ellen Wohl. Dr. Wohl was the first person that came to mind when we started to plan the agenda for this workshop. Ellen is a professor of geosciences at Colorado State University and leads up a team of incredibly talented people working on topics such as wildfire response, physical ecological interactions, carbon storage, large wood, and the effects of beaver activities. I'm always excited to see what is coming out of her research group because I know I'm going to learn something new and exciting. Professor Wohl is world renowned for her work on watershed process and is really pushing us forward in how we think about these systems and how they work and what we can do to restore them. She started her career working in geology and bedrock canyons and eventually branched out to mountain streams. She now focuses broadly on physical ecological interactions in river ecosystems and works in watersheds across the globe. Dr. Wohl has won a number of distinguished awards, including most recently the G.K. Warren Award from the National Academy of Sciences. Her work has real implications for the work we do to recover salmon and steelhead, and it is with great pleasure I introduce Dr. Ellen Wohl.
Thank you very much. That was a very gracious introduction. I'm going to give a brief overview of how I think about resilience in the context of physical and biological interactions. So that's what I mean by this kind of cumbersome word, the biophysical template. So I just wanted to define a couple of things so we're all talking about the same thing. Resilience is the ability to recover to pre-disturbance conditions. And I want to emphasize that it's not that a system is resilient or not resilient. It is a continuum that depends on time and space. And there are different parts of a river ecosystem, for example, that may be more resilient than others. And two of the systems in the Colorado Rocky Mountains, where I do a lot of my work, that are very resilient because they have a lot of spatial heterogeneity. So the upper one is a beaver meadow, the lower one is a channel with a lot of large wood. I'm using disturbance to refer to either something very episodic, like a wildfire, and that's the floods and debris flows that often follow, or it could be something that's continuing, such as climate change. And I use the phrase disturbance cascade to refer to changes in water and sediment and other materials that come into a river corridor after that disturbance. So a very, very simplified side view here. You're looking at a hill slope off to the left and then a valley floor with a couple of channels in the center. Whatever the disturbance is, whether it's a very intense rainfall or a fire, you typically have an increase in water and sediment coming into the river corridor. That then creates changes in a series of parameters: suspended sediment, the movement and supply of bed material, the channel geometry, both if you look at it in cross section and as you're looking at it from space and plan form, the living plants and animals, my highly artistic conifer trees here as an example, and the large wood that's forming log jams or just individual down pieces in the channel and floodplain. And fundamentally, these changes in water and sediment coming into the river corridor can strongly influence the three-dimensional connectivity of water and sediment within the river corridor. And I just put change because it can increase or decrease depending on the specific example. And I'm using this phrase river corridor to refer to the active channel, the adjacent floodplain, and the underlying hypereic zone. Because if you say river, most people just think of the channel. And I think it's really important to emphasize what we probably all are very familiar with, but a lot of people outside of science and engineering are not, which is that a channel doesn't exist in isolation. It's part of a system of these components of channel, floodplain, and hypereic zone, and they can have different levels of resilience. I think it also helps to emphasize the three-dimensional nature of the connectivity in the river corridor, if you speak of a river corridor. So there's that longitudinal or upstream, downstream, the lateral between the channel and floodplain, and vertical between the surface and the subsurface in hypereic or groundwater exchanges. And the river corridor, I think, is in many cases most effectively examined at a reach scale. If you're in a headwater channel, a reach may be only 10 or 20 meters in length. If you're in a large lowland river, a reach can be kilometers in length, but it's a continuous portion of the river corridor that has consistent geometry. So it might be between successive tributaries or between substantial changes in river valley morphology. And when I think of the influences on resilience at this scale, I think first of all of the physical configuration and stability of the river corridor. So Is the river corridor laterally confined? Do you have something like a bedrock canyon, or is it a fairly wide, low gradient area? And is it a steep or a more gently sloping downstream? You've then got the fluxes coming into that physical configuration. So water and sediment in all rivers, and in many rivers, either at present or historically, that are forested, there was large wood. And then interacting with those fluxes in physical context are biota. And I've just chosen beaver and riparian plants here, but this goes from salmon to biofilms to aquatic macroinvertebrates. There's a range of things that you can consider under this very broad category of biota. And then the other key components are just the space to adjust. So if you have a lot of water and sediment coming in, do you have a narrow, laterally confined system and everything just goes downstream faster? Or do you have places in the valley floor on the floodplain, for example, for material in transit to spread out, slow down, maybe be deposited if it's sediment, or infiltrate if it's water? And do you have the ability to adjust? So the extreme would be a concrete canal, which we have in many of our urban areas around the world. There's no ability to adjust. More comes in, it just moves faster. So there, you need space to adjust and you need ability to adjust to create this resilience. And particularly if you're working in high gradient or high relief systems, mountain streams, it's very common to see some pretty dramatic downstream alternations between what I've called strings and beads. And these are not my terms. They come from stream biologists working in the Northern Rockies in the 1990s, but they're very intuitive. A string is a laterally confined area. Think of something like a bedrock canyon. And a bead, as you're seeing in this illustration, is one of those wider, lower gradient areas where you've got the space to adjust, so accommodation space and the ability to adjust. And it's very common, I found in mountain regions around the world, to see a downstream alternation between these two morphologies. So just an example from the catchment that I'm going to use as an illustration in just a moment. That's a bead, and this is a string after a wildfire. So notice in this slide, there's minimal floodplain. It's really the active channel and just a tiny bit of floodplain on either side. So the example I'm going to use is Little Beaver Creek in the Colorado Front Range, or the Southern Rockies of the U.S. And I want to emphasize that everything I say here applies to rivers anywhere around the world. I'm just using this as a concrete example because I've worked here a lot, and I think it's easier to think about very, uh, sometimes very vague or abstract terms like resilience or response if you can see a specific case study. So this is a catchment of about 40 square kilometers. It had old growth montane forest. There were no active beaver dams here when I started working here, despite the name, but there were a lot of old beaver dams that are now vegetated berms. They're breached by the active channel, but they still are present across the floodplain. It's a snowmelt dominated system, but in late summer we get convective storms that can create flash floods. The big disturbance here was a wildfire in 2020. It burned 86% of this catchment, much of it at high severity. And as was very predictable, in 2021 and again in 2022, we had floods because of the effects of that wildfire. So this is what it looked like after the wildfire. These are pictures of the active channel and the riparian corridor. It's a small stream, and the fire was very intense, so it was scorched earth, literally. And then the flood in 2022 was much larger in magnitude. This is a portion of the river corridor that didn't burn, but is in the general catchment in the burn area. And this massive flood really redistributed a lot of large wood and created a lot of floodplain log jams. And you can see one of my grad students standing on one for scale. So just briefly to summarize, that we had the fire in 2020. The first runoff season was 2021. We saw snowmelt peak flow, and then we saw a series of small flash floods. Small compared to what came the next year, but they actually had higher peak flows than the snowmelt. They were very short duration, on the order of 5 to 7 hours. We had a lot of stream gauges that we had put in the system. So the 2021 edition of this disturbance cascade, the wide low gradient reaches were the places where there were more of these old beaver berms. They had trapped large wood in transport, and there was a greater density, a downstream distribution of channel spanning log jams in these reaches. Those channel spanning log jams facilitated overbank flow. And the overbank flow was erosive enough after the fire to create secondary channels. So you had a system of anastomosing developing. Basically, overbank flows were creating small secondary channels that would branch from the main channel and then join downstream in the beads where there was space for this to occur. We also saw more hypereic exchange flow and groundwater inputs in those areas, and that was based on the higher water table that was observed, more sediment deposition in those zones, and the fact that the floodplain regrowth of vegetation after the fire was much faster in the beads than in the strings. So at least one beaver came back um, and built some new dams that will further increase retention of material in these bead sections. So basically, the summary after the first summer was that we saw the bead reaches that had the greater space had more spatial heterogeneity. And I'm using that term to refer to anything that makes a river corridor different than a concrete irrigation canal. So the simplest way to get water downstream is to have a straight uniform channel that's rigid. There's no variability. As you have spatial heterogeneity associated with channels that branch and rejoin, with old beaver dams, with log jams, with variation in floodplain elevation, with pools and riffles, all these different sources of variation, that heterogeneity slows down the movement of material going downstream. And that material can be water, it can be solutes, it can be mineral sediment, organic matter. So I think of spatial heterogeneity, particularly in these beads, as promoting resilience because it's attenuating the fluxes of material moving downstream. If you think back to the disturbance cascade, you have an intense rainstorm or a fire, there's a lot more coming into the river corridor quickly. So if that all goes through like a fire hose, you're going to have big effects downstream. But if you can attenuate those fluxes and have some of that material move downstream more slowly, you're less likely to have major responses and often damage to infrastructure downstream. And I will say that in this summer of 2021, the catchment adjoining Little Beaver Creek also burned. That did not have these sources of spatial heterogeneity. It was a much more uniform catchment. It didn't have much in the way of beads. It didn't have old uh, beaver dams. That catchment in the same rainstorm that created these series of flash floods, or at least one of the flash floods in Little Beaver Creek, the other catchment had a major debris flow that killed 5 people and pretty much wiped out the fish population on the Poudre River, which both of these smaller channels are tributary to, for about 100 kilometers downstream. So there was a really substantial difference in response to the fire and the summer 2021 floods as a function of spatial heterogeneity differences in these two systems. Okay, so after 2021, I thought, oh, well, that's going to be the fire response. We're done. We'll just keep monitoring just in case. And this is why you do field work. I was very wrong. We had an enormous flood in 2022. I'm pretty confident in saying it's the largest flood that has occurred in more than a century in this system because I had a grad student who started working in Little Beaver Creek in 2014, well before the fire. At that time, it was old growth forest. There were no log jams on the floodplain, so there was no real competent overbank flow to create floodplain log jams. There were just log jams in the active channel. 2022, we had a flood that completely inundated the entire floodplain. And in the narrow reaches that created dramatic channel erosion, there was channel bed incision and bank widening, a lot of coarsening. So that's the response of the strings. In the beads, in those wide low gradient reaches, we saw a lot of material moving from the channel into the floodplain. So as I said, in 2014, there were no floodplain log jams. After this 2022 flood, we GPSed 600 floodplain log jams in an 8 kilometer reach of channel. And there were at least that many smaller accumulations of coarse particulate organic matter. Uh, Huge response of material moving out from the channel into the floodplain. Those log jams forced overbank flow. They created new channel avulsions of very small channels. What you're looking at here, the photo on the left, is flow going across the floodplain before it started to concentrate into a channel. And the little inset photo on the right is the flow spilling over the channel banks where it's returning to the active channel downstream. So it initiated a series of secondary channels and nick points that have been eroding headward. The flows, of course, have receded during the summer of 2023. We saw nothing comparable to this. But these floodplain logjams are going to be there for at least a few decades, probably more than a century, because wood decays slowly in this semi-arid environment. They're going to create nice habitat for a variety of riparian and terrestrial organisms. As the wood decays, it will probably influence soil moisture and soil nutrients under those sites. And there's this very persistent lateral connectivity that those secondary channels that were created during the 2022 flood are likely to persist based on what we've seen in other areas of the Front Range. So again, the net effect was that the spatial heterogeneity in this river corridor, mainly associated with those beads, really attenuated the downstream fluxes during this extreme flood and is continuing to attenuate downstream movement of material since the flood. So it's really promoting resilience in downstream reaches rather than concentrating this, again, this fire hose effect. So the valley segments that have that lower lateral confinement and greater spatial heterogeneity, those beads, are disproportionately important in attenuating those downstream fluxes of water, sediment, organic material. They're also, we haven't directly measured this since the fire. We did before the fire. They're disproportionately important in attenuating solute movement. We see more hypereic exchange in the beads, and in the part of the world that I live in, nitrate is an enormous concern. So facilitating hypereic exchange between the active channel and floodplain and the subsurface is very important for biological uptake of nitrate. Those wide low gradient sections are about 12% of this total valley length in the 9 kilometer reach we're studying, but they had a quarter of the total sediment storage in 2021 after that first summer of small flash floods and snowmelt runoff. We saw sediment and particulate organic matter, which is OM on the slide, storage in backwaters and secondary channels in overbank areas of the floodplain. We saw water storage in those same areas as well as in the hypereic zone. We also saw water storage in plant tissue. There was, again, a very fast regrowth of floodplain vegetation in the beads compared to the drier and more well-drained strings. And if we're attenuating sediment fluxes, then we are likely also attenuating phosphate fluxes because the phosphate tends to be adsorbed to the sediment. And if we're promoting hypereic exchange and backwater storage, again, we're enhancing nitrogen uptake biologically. And I would say that this creek is tributary to the South Fork Poudre and eventually the Poudre River, and all of these systems go into the primary drinking water supplies for this region, which are all surface water reservoirs. So I think sort of bringing it back to the context of this workshop and restoring watershed resilience, anything we can do to both protect and restore spatial heterogeneity within the most important reaches, which are, I would say, are those wide low gradient reaches like the beads, can really enhance resilience to the disturbance cascade. And I've mentioned the conflict or the alternate scenarios of what happened in Little Beaver Creek versus another system called Black Hollow, where we had the huge debris flow, loss of human life, big fish kill. There were intermediate small catchments. These are all on the order of 20 to 40 square kilometers that we looked at, a whole series of them. And one of the most interesting ones was one that was like Black Hollow. It was very steep. It didn't have much in the way of attenuation until the very last kilometer and a half of this catchment. Then there was a very retentive reach, and that catchment did not have a major flood and debris flow. So one good reach can make a huge difference in fostering resilience in these smaller catchments. So again, to recap, I think of it as you've got some physical template of these beads and strings. It's really set by the geology. It could be the glacial history in larger catchments. In the catchments I'm working in, they're below the elevation limit of Pleistocene glaciation. So the beads and strings are really a function of differences in bedrock fracture density as that influences weathering and erosion of the bedrock and the overall valley morphology. So you start with that. There's nothing humans can do to change that geologically induced spatial heterogeneity, but we can definitely influence what happens within that physical template. The biophysically induced spatial heterogeneity, log jams, beaver dams, different densities of riparian vegetation, we can either protect that or we can restore it if it's been lost. And the net result of all that is that we can influence the attenuation of these downstream fluxes in a way that creates greater resilience to post-fire disturbance cascades at the scale of individual reaches to larger river networks. One of the open questions that I and others at Colorado State University are working on right now is trying to use numerical models to say, well, how many of these beads do you need for different sizes of catchments and river networks? And does it make a difference where they're located in the network and exactly how heterogeneous they are? We don't know that yet, but we're working on that. And I know that other groups in the US or North America and Europe are also working on that. So again, I use this specific example from the Southern Rockies in the US, but this basic idea that spatial heterogeneity can attenuate the rate and the magnitude of material fluxes moving downstream should apply to rivers anywhere in the world, whether it's a tundra or the Arctic coastal plain or the smallest mountain catchment or a large lowland river in the Pacific Northwest. The general idea should apply to any river network. The most simplest way to express this is that the more spatial heterogeneity you have, typically the lower the longitudinal connectivity and the greater the lateral and vertical connectivity. So if you've got heterogeneity, there's places where things move downstream fast, places where they're moving downstream slowly because the material's spreading out into multiple channels, or it's going into floodplain wetlands, or there's obstructions like beaver dams or log jams. But those obstructions and the multiple flow paths can really create the pressure gradients that enhance hypereic exchange flows, so that vertical connectivity, and they can really create connectivity with other parts of the river corridor, such as the floodplain. And the forms of spatial heterogeneity can be as diverse as the rivers are diverse. So you can look at channel scale, so differences in substrate grain size, bed forms like pools and riffles or steps and pools, differences in the banks where you've got constrictions and expansions and undulations of the banks, differences in cross-sectional geometry at the scale of a reach, go alternating downstream between anastomosing or braided sections and single straight channels or meandering channels, the presence of log jams, beaver dams, differences in the type and density of vegetation, either within the active channel, if you're in a low gradient, fine grained system, or riparian vegetation in other systems, the presence of floodplain wetlands, and then scaling out to an entire catchment and river network. Uh, I've never seen, certainly in mountainous regions, anything that's a continuous bead all the way down a channel. But those longitudinal alternations between beads and strings or changes in valley geometry and function are another important source of heterogeneity. So I think fundamentally, we need to identify what's there, what could be there naturally, what are the processes that create and maintain that heterogeneity, whether it's, if you're looking at log jams, having a forested riparian corridor with sources of wood that can be recruited into the channel and floodplain. There are other processes and sources of heterogeneity in different settings. And then what are the potential thresholds? So this gets back to that idea of how much and where. If I hold up my hand here, if it's centered on the camera, my fingers are the different tributaries to the main stem that would be my forearm. Now, do we need one bead here, maybe another one here, or do we need 6 beads on each of those tributaries? So there are undoubtedly thresholds in terms of the response of the system, and I think that numerical modeling combined with field measurements can help us start to understand that. And then fundamentally, we need to develop management strategies, either to protect the fairly functional and intact river corridors or jumpstart here. I'm thinking of there are a lot of studies that show it takes 200 years to go back to natural wood loads once an area is clear cut. We don't have 200 years. So engineered log jams, reintroducing large wood, the manner that's done with some of the stage zero restoration projects in the Pacific Northwest, they can help us facilitate or accelerate that process of returning to heterogeneity. And I think there's really a role for both field-based measurements to calibrate and verify some of these models, remote data collection. We have to think about what we're doing, so conceptual models, but also numerical predictive models. So there's a lot of opportunities for the research community to work with practitioners to better understand and manage these systems. And with that, thank you very much. And I think we have time for questions, so I'm happy to answer questions.
Thank you so much, Ellen, for a really rich talk that took some very complex information and I think rolled it out in a very coherent and clear way for all of us to follow, and some great visual analogies there with beads and strings. No surprise, we have lots of activity in the Slido and lots of great questions coming in from our audience. And so we're going to jump right into questions because I know there's lots of people wanting to hear your thoughts on a number of issues here. I'm going to start with the top question. We've got 8 likes, so it's clearly something that's resonating with many people here today. Might we need to reconsider the resilience definition, being recovery to pre-disturbance conditions, in a world with shifting baseline conditions? Could resilience be instead considered the ability to respond to disturbances without loss of ecological function? Any thoughts on
Absolutely.
that?
Excuse me, there are a lot of definitions of resilience out there, and I chose one just because I didn't want people to spend the whole talk wondering exactly what I meant by resilience. But yes, I completely agree. In most cases, we can't go back to some, I don't know, pre-European reference condition in North America. So however you're going to define ecological function, talking about resilience in terms of preserving or restoring some variety of or some aspect of ecological function, I think is a very good way to think of it. The other thing I would just add is that I'm actually starting to use a different phrase rather than resilience. It's a mouthful and it's kind of cumbersome, but it's absorbing capacity, and it refers to specifically the physical ability of the system to absorb disturbance and continue to function. And that function could be defined in terms of physical characteristics or biological communities or ecological.
Yeah, that makes a lot of sense. Thanks for that. I think in thinking about that absorbing capacity of a system, I often think of that as absorbing the water and the material that might be moving through in big flood events, per se. The top question right now is asking, would you say that same concept applies to resilience to drought and low flow conditions in the same way that it more obviously applies to flood events?
Yeah, I would still bring it back to biophysical spatial heterogeneity, because if you're slowing down the movement of materials through the river corridor, you're also storing it. And it flashed by pretty quickly at the beginning of my talk, but I had a picture of a very complex beaver meadow in Rocky Mountain National Park. And I've come to think of that thing as bomb-proof because it does really well when there's a fire. And Emily Fairfax's work on beaver meadows has shown this really nicely. You have a high riparian water table. You have a lot of standing water at the surface. You have a lot of water in the vegetation. So it's an environment that's a good fire break. It stands up for the same reason if you have very dry or low flow conditions, like prolonged drought, and people like Glynis Hood, no, I don't know the first name, Hood and Bailey, I know, and Sherry Westbrook have shown this in Canada, that those areas with a lot of standing water and high water tables and wet vegetation, as you would expect, are much more resilient to drought. And that particular beaver meadow that I showed a photo of showed almost no effect in the flood of record in this area, which was in 2013, and other parts of that river, it's the North St. Vrain Creek, had major, major changes. But if you think about a beaver meadow that's a dense willow carr, that's CARR, dense willow wetland with multiple channels and ponded water, the flood got to the upstream end of it and just went, just lost all its momentum because there was such a high hydraulic roughness across that whole floodplain. So I think spatial heterogeneity can increase resilience to a variety of characteristics, whether it's high flow, low flow, extreme heat, chemical contamination too. If you have some toxic material entering the river corridor, if you can sequester some of that material in the floodplain, it may not be good for that part of the floodplain, but it's going to help downstream areas a lot.
Great, thank you. I'm going to grab the second question that I at least see on my screen here. Is I was curious as well. Your talk emphasized spatial heterogeneity and the importance for watershed resilience, and also this idea of the bead and string and this attenuation of material and water moving through a system. And so the question is, if the whole system had room to move around, let's say the whole system basically was an elongated bead, would that be as beneficial to resilience as, say, the idea of the bead and string with these interspersed confined and unconfined reaches? Have you teased that apart in any of your work?
I think so. I think it would be more beneficial. And there are lower relief environments where what I and others have called river wetland corridors were far more common. I mean, using a U.S. example, the most famous one would be the Everglades system. That was one giant bead, or parts of some of the coastal rivers. I'm thinking of the Willamette in Oregon. There was a very continuous floodplain wetland complex all along those historically, and the more the better if it's natural. If you go back, I haven't done this so much for Canada, but certainly in the US, if you go back and read the first written descriptions by people of European descent, whether it's in the southeastern US, the Northeast, the northern Midwest, all they do is moan about how hard it is to find the river and to follow it, whatever river it is, and whether they're going up or downstream. There's all these obstructions of wood rafts, naturally occurring wood rafts, log jams, beaver dams, wetlands. The channel's branching. They can't figure out which is the main channel. I think we have a very distorted view of what many lowland and mountain rivers look like. And I think there were much, much longer and more continuous beads. In a paper a long time ago, I referred to this as the Great Drying, that people of European descent have systematically dried out the landscape through channelization, through groundwater extraction, through flow regulation. So we underestimate how much more prevalent very wet and longitudinally disconnected river corridors were. The more we could go back to that, the better for resilience to a variety of disturbances.
Great, that's really helpful. We'll take the top question here, and we're going to hear the word resilience a lot through the course of today. Is there a specific metric of resilience that we should be trying to include in our own monitoring and our own studies, or do we rely on a variety of measures of spatial and temporal heterogeneity? Do you have some guidance on that for us?
No, that's the most difficult, but also I think one of the most important questions you could ask. Mm-hmm. There is no single metric of resilience. There are a lot of proposed metrics. And these range from things like the number of feedback loops that you've got in a river corridor or river ecosystem, and therefore I suppose you could say the absorption capacity in a biophysical sense, to metrics of spatial and temporal heterogeneity. There's no consensus. And I don't think there's going to be for a while. I think it's a very important question, and it's one that needs to be explored. I have a paper that is in press at Bioscience about resilience, and we have a long supplemental section in there where we have about 4 pages of summarizing, and there's 4 co-authors who are geomorphologists and ecologists, and we were trying to think of all the things we could think of that you could potentially use. Spatial and temporal heterogeneity is a good starting point. It's not enough. That's like, how are you going to define or measure ecological integrity? There's a lot of different indices that have been proposed. So it's something we have to keep working on, but there's no consensus yet.
Great, thank you. We've got a question that's been hovering at the top there for a while. It says, in your career, have you ever encountered cases in which spatial heterogeneity was not good for resilience? Or would you say that there's always a very strong correlation between that spatial heterogeneity and resilience piece?
I always hate to say no, never. This is so absolute, and there's always exceptions. But I cannot think of any place that I've worked or that I've visited where it wasn't a good thing to have spatial heterogeneity. I mean, there's spatial heterogeneity that's introduced by humans, like a dam in a canyon river could be a form of spatial heterogeneity. But if we're talking about naturally occurring spatial heterogeneity, I can't think of an example where that didn't help.
Great. Yeah. That makes sense. So that's kind of the benchmark we're all aiming for in our projects. What actions could agencies take on public land that's inexpensive to improve heterogeneity before a fire and after a fire? I think you could extend that to not just in a fire situation, in a drought situation as well, but that idea of like what actions can we implement fairly efficiently without a high cost to start working towards a more heterogeneous system.
Well, one thing is, I said we can't change the distribution of beads and strings, but you can have a bead that's just a flat surface that's grassy and a channel that's incised below it, and the banks are stabilized. So you can have the bead form and it's not functional for a variety of reasons. So beforehand, removing anything that limits the ability to adjust and that three-dimensional connectivity within the river, and actively restoring some of that. If you're in a forested region, putting large wood back in. If you're in an area that would naturally have beaver, trying to do things like grazing exclosures if there's grazing pressure that's limiting the beaver from coming back, trying to hydrologically reconnect the channel and floodplain so the riparian water table goes up and can support the type of woody vegetation that beavers use. I'm not going to keep going through examples because it's very site specific, but I think there are things that you can do both beforehand to increase the resilience and increase the spatial heterogeneity, and then you can do those same things after. What is going on very widely right now in the Colorado Front Range after those 2020 fires, which were the largest in the state's history thus far, is a lot of beaver dam analog construction, engineered log jams, basically trying to introduce obstructions and slow down movement of material. In some places, it may be, if it's possible, acquiring land. If you have people with infrastructure in the river corridor, trying to remove that infrastructure and get those people, with a buyout or get them to move someplace less hazardous. Sometimes there's a window of opportunity after what is often called a natural disaster, when people's property has been destroyed and they may be more open to the idea of moving out. And the same thing with public land agencies. Oh, well, the culvert just failed completely, or the bridge. Can we think about how to redesign this or potentially move it elsewhere if that's feasible? So I think the short answer is yes, there are things you can do before and after.
Right, that touches actually on a few other questions that are popping up in Slido around how to persuade or how to have that conversation with property owners around increasing heterogeneity on their own lands. Yeah, go ahead.
Just say one thing quickly in relation to that. I have a talk that I give called Messy Rivers, and messy is just a shorthand for spatial heterogeneity. And I've given that a lot of times, including to homeowners associations here in Colorado, and it's very well received. People want to do things differently, and they don't want to be so vulnerable to natural disasters if there's anything they can do about it. So if you're going to use jargon like spatial heterogeneity, three-dimensional connectivity, just explaining it with visuals and with different words, I found that people are pretty open to that and very receptive.
Great. Yeah, that's helpful. I know in the world of wetland restoration, they often use the term rough and loose when we're trying to convey what sort of a spatially heterogeneous landscape would look after a successful wetland restoration. It's not necessarily aesthetically pleasing but it's really the look we're trying to achieve. We're going to squeeze in one more question. I know we're running out of time, but there's just so much interest in your work, understandably, and it's controversial. Well, not controversial, but beavers are a hot topic. Lots of us are encountering BDAs and other beaver-themed restoration projects in our work. Can you comment on the mass removal of beavers from rivers and streams in the Rocky Mountains, but really widespread across Western North America, and that idea that without beavers, stream heterogeneity is much more difficult to reestablish? So it's a loaded question. We've got a short amount of time, but your thoughts to finish up.
The simple version of the mass removal was a disaster in terms of rivers as ecosystems and storing water and sediment and nutrients on the landscape. Beaver were not present everywhere historically. They shouldn't be reintroduced or mimicked everywhere. They don't build dams in canyon rivers, for example. And I say that partly in jest, but I've seen people trying to do that. So being aware of the biophysical context where you're trying to reintroduce heterogeneity. But the more we can do to either mimic beaver or ideally restore them, because they are self-maintaining if they've got a food supply and they can live in a place, I think that's beneficial. That's being done in the UK and Western Europe as well. The only place beaver are bad is Tierra del Fuego.